They are mind-bending, fascinating, and a little bit terrifying. Ready to go deep into what they are and what they might be capable of? Here we go. In the vast cosmic tapestry that unfolds across the heavens, there exists a classification of civilizations that transcends the boundaries of our earthly understanding, the Type II civilization. Coined by the renowned astrophysicist Nikolai Kardashev, this classification delves into the hypothetical realm where society harnesses the entirety of the energy radiated by its star. As we ponder the implications of such a civilization, we are compelled to embark on a cosmic odyssey, exploring the uncharted territories of technological prowess and societal evolution. Type II civilizations are hypothetical civilizations that are so advanced that they are able to harness the energy of an entire star. Yes, an entire star. This is known as a Type II Kardashev civilization, named after Russian astronomer Nikolai Kardashev.
A Type II civilization would be able to do a lot of advanced things which we're going to be talking about in this video. Come with us. Over time, we must have heard about a couple of civilizations that talk about advancement and a Type II civilization is one of them. As a method to measure and classify the technological advancement of a civilization, Soviet astronomer Nikolai Kardashev conceived of the Kardashev scale in 1964. In its early formulation, the Kardashev scale was based on the overall consumption of energy, assumed equal to the total energy supply of a given civilization. Kardashev defined three distinct types of civilizations. A Type I civilization is referred to as a planetary civilization. Characterized as having a power consumption of 10 quadrillion watts, a civilization of Type I has harnessed for its use all major forms of energy available from its home planet, for example human civilization and the Earth. Of course, this also includes the energy received by the home world from its parent star. Planetary energy sources humanity can tap include fossil and bio-derived fuels, nuclear energy, wind, solar, geothermal, and tidal, among others. A Type II civilization, also referred to as a stellar civilization, consumes 10 quadrillion watts to achieve a 10 order of magnitude increase in power consumption over Type I civilizations. A Type II civilization must be able to obtain and store all the energy its parent star releases. Of course, a Type II civilization can also take energy from its planetary system as well. To achieve such a colossal degree of energy capture and consumption, immense constructions would all but certainly need to be engineered and built. For example, a Dyson sphere, Matryoshka brain, or other forms of planetary system networks, or starlift, also called stellar mining, stellar engineering, or astroengineering. The Sun's total energy output, its luminosity, is approximately 4 gigavigintillion or 4 by 10 raised to power 26 watts. If human civilization can capture more than 1/4 of the Sun's overall energy output and use it efficiently, ours will qualify as a Type II civilization. Other more exotic energy sources of Type II civilizations may include extraction from black hole accretion disks, and jets or matter-antimatter annihilation. As an approximation to the more familiar, it can be estimated that to obtain 1 gigavigintillion watts, the water mass contained in approximately 14,700 typical backyard swimming pools, typically 20,000 gallons each, would need to be annihilated every second, assuming 100% efficiency in converting mass to captured energy. A Type III civilization is also called a galactic civilization. With an energy consumption of 10 sexquinquagintillion watts, a civilization of Type III can access and control much of the energy the entire galaxy that civilization lives in generates. Homo sapiens hasn't even reached Type I on the Kardashev scale. An actual Type I civilization would already make short work of us. They have complete control over their planets, and have the potential to cause destruction on a planetary scale. A Type II or III civilization, however, now that's overkill on a pretty big scale. A Type II can harvest energy from stars themselves, meaning they could control our sun and use it as an energy resource. A Type III can do everything a Type II can, on a greater scale that is, they can control the energy of an entire galaxy. Safe to say that we don't even have a hair of a chance so far. A Kardashev Type II civilization is a civilization able to use all or most of the energy of its parent star, most likely through the use of a construction like a Dyson sphere or a Dyson swarm. A Dyson sphere is a hypothetical, large mechanical structure, a megastructure, designed to harness the energy of stellar nuclear furnaces. The basic idea is that a structure is constructed around a star which converts, stores or otherwise utilizes the star's radiant energy. These facilities are postulated as the most likely, necessary and economical way of addressing the colossal energy needs of both future human civilization and, possibly, advanced alien civilizations elsewhere in the cosmos. The purpose of a Dyson sphere is to harness the colossal energy released by the host star. We already have the basic technology to do this, in the form of solar cells. These use a process called the photovoltaic effect, whereby photons knock electrons out of atoms, thus creating a separation of charge within a material, resulting in an electric current. Dyson spheres, whatever their form, are likely to use this process for the generation of energy. Some researchers envisage this energy being transferred by some form of wireless technology to the nearby civilization, probably on a habitable planet in orbit around the host star. Although there is, as yet, no evidence that Dyson spheres, or anything similar, exist anywhere in the universe. However, scientists can say something about whether they are allowable. Firstly, although such technology is way beyond what is currently possible for Earthbound intelligence, there are no known insurmountable barriers to their construction. Given enough incentive, resources and technological advancement, Dyson spheres are certainly possible. One researcher estimates that humans could attempt such a feat within the next 100 years or so. Other researchers claim this is wildly optimistic. Astronomers have actually placed some limits on how many Dyson spheres may be lurking out there in the cosmos. To do this, some assumptions are made about how these structures would affect the emergent starlight of the stars they surround. For example, most designs would block some of their host stars' light, leading to a drop in their optical brightness. They may also result in waste heat that would be emitted as infrared radiation. By looking carefully for such deficits or excesses in the light of thousands of stars, one estimate suggests up to 10,000 stars could host Dyson spheres within a radius of about 16,000 light-years of Earth. By comparison, the distance to the Milky Way's center is about 26,000 light-years. You might be wondering how one could build a Dyson sphere. Well, one possibility, as the name implies, involves the construction of a spherical framework around a star, usually called a Dyson shell. To control the effects of the star's gravity and radiation pressure, such a structure would probably need to be both flexible and have a propulsion system to alter its position. Some researchers suggest, however, that maintaining stability in such spherical structures may not be possible. Dyson spheres might probably not be spheres at all. Some concepts envisage ring structures, dense swarms of orbiting satellites, or swarms of statites, also called static satellites, that remain motionless with respect to the star, called a Dyson bubble. Engineers have proposed that these structures could be built remotely by armies of spaceborne robots and that the materials for construction can be obtained by dismantling terrestrial planets. Other more exotic forms of Dyson structures have also been postulated, such as galaxy-sized clouds of smart dust that harness the energy of billions of stars. The primary purpose of Dyson spheres, if ever constructed, would be to harvest the immense energy output of a star. This energy could then be utilized for various purposes, including powering the energy-hungry needs of an advanced civilization. Dyson spheres could support vast ecosystems, advanced technological developments, and sustain the energy requirements for activities on an unprecedented scale. The energy captured from a star within a Dyson sphere could be converted into various forms, such as electricity, to meet the power demands of advanced technologies, space exploration, or even to facilitate the needs of a highly populated interstellar society. In essence, Dyson spheres represent a conceptual solution to the ever-growing energy demands of an advanced civilization by tapping into the colossal energy reserves of stars. The level of technological development of any civilization can be gauged in large part by the amount of energy it produces for its use, but also encompasses that civilization's stewardship of its home world. Following the Kardashev definition, a Type 1 civilization is able to store and use all the energy available on its planet. In this study, we develop a model based on Carl Sagan's K formula, and use this model to analyze the consumption and energy supply of the three most important energy sources: fossil fuels, nuclear energy, and renewable energy. We also consider environmental limitations suggested by the United Nations Framework Convention on Climate Change, the International Energy Agency, and those specific to our calculations, to predict when humanity will reach the level of a Kardashev-scale Type 1 civilization. Our findings suggest that the best estimate for our civilization to attain Type 1 status is within the common calendar year range of 2333 to 2404. The Kardashev scale is a method of measuring a civilization's level of technological advancement based on the amount of energy it is capable of using. The measure was proposed by Soviet astronomer Nikolai Kardashev and was named after him. The scale is hypothetical and refers to energy consumption on a cosmic scale. Various extensions of the scale have since been proposed, including a wider range of power levels, types 0, 4, and 5, and the use of metrics other than pure power. In summary, for the entire world population to reach the status of a Kardashev Type 1 civilization, we must develop and enable access to more advanced technology for all responsible nations while making renewable energy accessible to all parts of the world, facilitated by governments and private businesses. Only through the full realization of our mutual needs, and with broad cooperation, will humanity acquire the key to not only avoiding the Great Filter, but continue our ascent to Type 1 and beyond. According to the Soviet astronomer, our civilization would be too young to be able to contact another civilization that would certainly be more advanced than us. The solar system is too young with its 5 billion years, and the first ancestors of today's man appeared only 6 million years ago at the earliest. The oldest celestial objects are between 10 and 14 billion years old. It is clear that the other civilizations are incomparably older than the human civilization. Therefore, the knowledge of these civilizations must be greater than ours, and, he reasoned, they must surely be aware of what we are doing. Now let's talk extensively on Type 2 civilization. Type 2 or K2 civilization has control over their solar system, and may be able to harness the power equivalent of a single star. It extracts fusion energy, information, and raw materials from multiple solar systems. It is capable of evolutionary intervention, interstellar travel, interstellar communication, stellar engineering, terraforming, and star cluster scale influence. The resulting proliferation and diversification may negate the probability of extinction. Complete control of the fate of its home planet where threats like ice ages and global warming can be avoided. A possible utopian outcome on the low to mid-end of the K scale is the Dyson sphere, a hollow gigantic shell with a surface area equivalent to millions of Earths that can fully enclose the Sun and capture all of its solar energy output. Under the direction of a godlike superintelligence, huge numbers of automated, self-replicating ships can build it using material from the asteroid belt, the Kuiper belt, and the Oort cloud. The interior walls will have a gravitational field similar to Earth's and will use magmatter to withstand the immense tensile forces required to maintain structural integrity. Portions of this sphere have stable atmospheres, oceans, and land masses, and are a habitat for many sapient life forms, including biological humans, transhumans, aliens, and androids. With digital immortality, many humans live in massive, hyper-realistic simulations. Others are using synthetic and biological bodies created for them in the physical world using advanced versions of nanotechnology and programmable matter. A Type 2 civilization would use the same techniques employed by a Type 1 but applied to a larger scale. In 1960, physicist Freeman Dyson famously suggested that an advanced civilization could harness the energy of its star by building a massive system of satellites that enclosed it. These megastructures, commonly referred to as Dyson spheres or Dyson structures, said Dyson, could be searched for by looking for large infrared signatures, the resulting heat radiated by these megastructures. It has also been suggested that a Type 2 civilization would also be capable of star lifting, where they can reposition stars. A possible method for doing this is a variation on a Dyson structure known as a Shkadov thruster, or stellar engine, that partially encloses a star and uses its radiative force and gravitational attraction to achieve momentum and even relativistic velocities, which could be an explanation for some hypervelocity stars. However, much like the similar Drake equation, the scientific value of the scale is more qualitative than quantitative in that it summarizes the challenges SETI researchers face. At the same time, the scale is encouraging since it shows that the existence of a single Type 2 civilization in our galaxy would not go unnoticed forever. As Kardashev noted in the final section of his paper, which addressed the implications of his scale,
the estimates arrived at show that should there exist even one Type 2 civilization within the confines of the local system of galaxies, there will be a realistic possibility of securing an enormous quantity of information. The same holds for the existence of even one single Type 3 civilization in the portion of the universe accessible to observation. Finally, it is entirely reasonable to assume that Type 2 and Type 3 civilizations would be in possession of information many orders of magnitude in excess of what we have available at the present time. For that reason, they would have to be broadcasting practically continually, and this would also be the case for increasing the possibility of reception by Type 1 civilizations.